So now we're going to continue on with descriptive statistics. Now we're going to look at measures of central tendency. These are values that describe the center or a typical value. We're going to be looking at several different types and then eventually looking at shapes of data sets. So measures of central tendencies are values that represent a typical or the center or middle of a data set. The three most common are the mean, the median, and the mode. The mean is what we're going to look at first. Most of you know the mean by its other name, an average. Most of you know how to find an average. You sum all of the data values and divide by the number of data values. Let's look at this notation. This is known as sigma notation. This symbol here is the capital S in the Greek alphabet. It stands for sigma, or sum. It denotes the word sum. Sum all the x's, add up all the data values x. Now remember from chapter 1, we have population parameters and we have sample statistics. Most of our population parameters are going to be denoted by the Greek alphabet. This is the lowercase m in Greek called mu. So mu denotes the population mean, and it is found by summing all the values in the population divided by capital N, the number of values in our population. The sample mean is denoted by an x bar, known as x bar, and it's, again, sum all the values in our sample divided by lowercase n, the number of values in our sample. Let's look at an example, finding a sample mean. Here we have 7 different fares to Cancun, Mexico. How do we find the mean or the average? You would add up all the values and divide by 7. So we add, this symbol here, remember, is sigma notation. Sum all the x's, sum all the values, and we get 3,695. There were 7 fares total, so 3,695 divided by 7 is approximately 527.9. So the average price of a flight is about $527.90. The next measure of central tendency that we're going to look at is the median. The median is the value that is in the middle of the ordered data set. It is a value such that half of the data set is smaller than that and half of the data set is larger than the median. If we have an odd number of entries, the median is actually the middle value. But if we have an even number of entries, there will be 2 middle values, and we're going to average those 2 middle values to find the median. Back to our example with the 7 flights. First thing we want to do is order the data set. We ordered the data set. We have, this is the number in the middle, 3 numbers smaller, 3 numbers larger. Thus, the median is 427. 50% of the values are smaller than it, 50% of the values are larger than 427. Suppose we take one of the fares away. Now we only have 6, which is an even number. We order the data set again. Now we have 2 middle numbers. We're going to add these 2 numbers together, divide by 2, and that will give us the median. So the median is 412, which is a value such that half of these numbers are smaller than 412 and half of these numbers are larger than 412. So the median price of a flight is $412. The last one we're going to look at is the mode, and it is the data entry that occurs with the most frequency. If no entry is repeated, then we say the data set has no mode. But if we have 2 entries that occur with the same greatest frequency, we say that the data set is bimodal. Again, we go back to our data set. Often it is easier if we go ahead and order the data so we can put all the numbers together. Here we see that 397 is listed twice. Thus, my mode is 397. The mode of the data set. Mode is mostly used with qualitative data. It is the least common, it is the least informative. between the mean, the median, and the mode. The mode is the only one that can be used with qualitative data. The mean and the median must have quantitative data or numeric data, and the mode is used with qualitative data most often. Okay, so continuing on, here's an example of a mode using qualitative data. We have political party affiliations. Since Republicans are represented the most, we see that Republican then is our mode. And comparing the mean, the median, and the mode, you are most likely going to be using the mean unless we see, because it has the advantage of using all of the data values. In fact, it's required for many of our inferential tests that we're going to see later. It's very reliable, but its advantage is that it's greatly affected by outliers. Most of you know already from school that if you are an A student and all your grades are A's, and one time you will go in to take a test and you're not feeling well and you make a 30%, you just performed horribly, that 30% does bring your average down, but it would not change the median. So if we have an outlier, the mean is not always the best measure of a typical data value. Let's look at this data set. We have ages in a class, and most of these students are in their early 20s, except for this one 65-year-old. Now, this isn't known as an outlier because it is significantly higher than all the rest of the values. An outlier could also be significantly lower. If we calculate the mean, we see that the mean age is almost 24, whereas that's the largest age before we hit the 65-year-old. The median is a better measure in this case. 21 and a half years old seems to be a typical value. The mode is 20, but again, that's the youngest age. So again, it's not a great measure of a typical value of this class age. Right? Mean takes every entry into account, but it is influenced by that outlier of 65. The median also takes every value into account, and it is not affected by the outlier. Because of the outlier, the median would have been the better choice. And the mode exists, but it does not appear to represent a typical entry. All right, now, if we graph this, we see there's this huge gap. That's distinguishing that outlier from the rest of the data set. Next, we're going to look at what's known as a weighted mean. A weighted mean is the mean of a data set whose entries have varying weights. We see this often. The most common one that you're used to is your GPA. When your GPA is figured out, a B in a 4-hour class is going to have more quality points than an A in a 2-hour class. So to find the weighted mean, you take each value times the weight that is given to that type of entry and sum these values up, divided by the total sum of the weights. So let's look at an example that you're kind of used to. Suppose in your class your grade is determined from 5 different sources. Your test grades, your midterm, your final exam, your computer lab work, and your homework. Suppose you get an 86 is your exam average. You get a 96 on the midterm, an 82 on the final, 98 on your computer lab work, and 100 on your homework. Let's figure out your weighted average. So we take your test times its weight of 50% and get a 43. 96 on your midterm times its weight of 15, and we get a 14.4. Your final exam grade, 82, times the weight of 20%, written as a decimal, 0.20, and we get 16.4, and so forth. We add up the sum of the weights. When we add these up, we get 1. Doesn't always work. That not all weighted means have a sum of the weights adding to 1. And then we add up each of the types of grades times their weight and get 88.6 divided by the sum of the weights, and your grade is an 88.6. You're close to an A, but you did not quite get the A. We're going to skip the mean of group data, so let's just skip through these slides. And now we're going to pick up again with the shapes of distributions. The first shape we're going to look at is known as symmetric data, or a symmetric distribution of the data. Symmetry happens when you have the middle. If you take the graph and you fold it down the middle, the two sides match. This is similar to what you see when you see a butterfly. You folded a piece of paper in the middle, you drew one wing, and then you cut out the wing, opened it up, and you had a butterfly. Butterfly is an example of symmetry. In symmetric data, the mean, the median, and the mode are all equal to each other, and they're all equal to this value right in the middle. Uniform data is also symmetric, so the mean and the median are also right in the middle. If we fold along this middle line, we would get it matching on both sides, but there is no mode. Right, the mean and the median are still equal to each other, but there is no mode because no value appears more often than the others. Skewed left data. Now, skewed left data has to do with the tail. This is known as the tail. The tail of this data is on the left. It's where we have this long set of very, very small frequency. In skewed left data, these outliers over here pull the mean down. So in skewed left data, the mean will always be less than the median, and the mode will be still the bar with the highest frequency. Examples of skewed left data would be life expectancy. Some people die young, but most of us live a full life and we die over here, and a few of us live to be the 115 or whatever. Skewed right data, also known as positively skewed, the tail here is on the right side of the data. In this case, the tail pulls the mean down. In skewed right data, the mean will always be greater than the median. The mode, again, is the bar is located with the bar with the highest frequency. Data examples of this would be income. Very few poor people. Most of us are here in this low to middle income, and then this tail is caused by the very, very wealthy in our society. So we are now at the end of section 2.3. You should be able to calculate the mean, the median, the mode of both populations and samples. You should be able to find the weighted mean of a data set, but you will not be asked to find the mean of a frequency distribution. And you should be able to describe the shape of distributions as symmetric, uniform, or skewed, right or left, and compare the mean and the median for each. It's now time to go to my math lab and do homework 2.3.